Yeah, thank you very much. Of course, I'm thrilled to be able to give this talk and recognize that this award is also an award for the whole field of high-energy nuclear physics. What I would like to do is, rather than give a complete account of what was actually done, I would like to make a few brief remarks on introducing the subject, the LHC era and relativistic nuclear collisions. Then I will briefly touch on what we call the hadron resonance gas, because that turns out to be an important development of the last year or last years. I will show you how we actually arrive at an experimental delineation of the phase boundary between the quark-gluon plasma and the hadronic phase we all live in. And then I will comment on something rather peculiar, namely what we call the paradigm of loosely bound states. This is part one of the Stern-Gerlach-Medaille presentation. Johanna Stachel will extend the considerations also to take account of heavy quarks. So before I start, I should say that, of course, this work we did not do all alone. There are very strong contributions, in particular on the phenomenology results from a long-standing collaboration with Anton Antonik and Krzysztof Redlich and, of course, Johanna. And most of the data you will see, because I will focus on that, come from the high-precision work of the ALICE collaboration at the CERN LHC. And, of course, we are very grateful for all the support and help we got from that collaboration. I should say that there is also a paper beyond what is in this Nature paper here, which will become important as we go on. Just to show you that this collaboration is real, here is a picture of what we call the Gang of Four, since 20 years, still going and still a pleasure. Now, let me very briefly introduce the subject. I have sketched here the timeline and matter in the early universe. There are many uncertainties as we go to earlier and earlier times. In fact, inflation actually could end up at 10 to the minus 32 seconds, but it also might last a lot longer. But what we certainly know is that around 10 to the minus 12 seconds, there is an electroweak phase transition. The phase transition around a temperature of 100 GeV, and remember the early universe is practically at all times in full equilibrium, so talking about temperature makes sense. During that time, of course, the C's, W's, and the Higgs and others acquired their mass, and it is the period between 10 to the minus 12 and 10 to the minus 5 seconds that the early universe is thought to have consisted of what they call a quark-gluon plasma phase, in which all along in equilibrium, including photons and neutrinos, which of course in our experiments are not in equilibrium, so there is a different phase. But during that time, we essentially have more or less free quarks and gluons, and it's this phase which you would like to study with nuclear collisions. Afterwards, of course, there is this famous phase, annihilation and light element production, on which I will not comment any further. Now, this is sort of pictorially introduced once more. We collide two heavy nuclei at LHC, they are very dramatically Lorentz contracted. So the collision takes place at an instant at something like a 100th or a 1,000th of a Fermi timescale, with a very large initial energy density. I will comment on how large this has to be. This QGP phase will form and eventually expand and cool such that there is a transition to hadrons. These are the constituents of what we call the hadron gas. So it consists of familiar particles, pions, kaons, protons, but of course also photons and lepton pairs. And it's those which we actually measure. And the idea is that out of measuring all of those particles, their momenta and identity, that we would like to understand what the state of this matter has been, at least at an instant when particles are produced. Now, this is, of course, a formidable task. This, on the right-hand side, is not a Monte Carlo simulation, but is actually one of the first events we saw in 2011. And it contains something like tracks for 3,000 particles. And these are all charged particles. We measure them all. And we'd like to reconstruct the state of the system from those tracks, and I will show you how. This is once more, but now we go to the full energy at the Large Hadron Collider. November 2008, 5 TeV per nucleon lead-lead collisions. Let me just say that in such a collision, if you integrate over all of space, there are more than 32,000 such hadrons produced in one collision. And so you can imagine that thermodynamical concepts make sense even event by event. And this, of course, is some of the areas where we are actually working on. And I will show you what kind of regularities we can get out of that system. But before, of course, you have to build these detectors. This is a picture taken inside the ALICE time projection chamber before it was closed. You see here for the insiders field cage, the outer field cage, and the inner field cage, and practically all of this had to be done by hand. The whole detector has 560,000 channels, readout channels, each with 1,000 time bins. So you have 560 million pixels, if you like. And we actually plan to run this, we have run this detector at 10 kilohertz readout. And in the next few years, this detector, appropriately modified for the readout chambers, will run at 50 kilohertz. Now, we have actually benefited from dramatically good performance of the Large Hadron Collider. Actually, Large Hadron Collider has worked beyond design, significantly beyond design luminosity, in particular also for heavy ions. And we have actually, in the last campaign in 2018, acquired something like 150 million very central events. Not all of that is analyzed by now, but some of it is analyzed, and this analysis will be completed in the next year or so. Now, how do we manage to determine which particle is which? There is a whole sequence of identification detectors in ALICE. I show you here again the time projection chamber with a specific energy loss on the vertical axis and the momentum of particles measured in the magnetic field on the horizontal axis. And you see how nicely electrons, muons, pions, kaons, protons, neutrons, and so on are separated. I should say this is now the PDG, the particle data group standard, and has made its way in the PDG, if you are interested, figure 34.15. And of course, we're very proud of that. So, to get into physics, hadron production and the QCD phase boundary. As I said, we measure momentum and identity of all produced particles. Actually, I will show you mostly top LHC energy, but of course we, meaning the whole field, has measured this from low energy all the way to LHC energy and look for signs of equilibration, phase transitions, regularities, and so on. Now we have some guidance from Lattice Qcd, that is solving the QCD Hamiltonian on the discrete space-time lattice. And what is shown here is thermodynamic quantities from such simulations. Temperature is here, and on this axis is plotted, let's say, for energy density blue, the energy density in units of T to the 4, so that actually is a measure of the number of degrees of freedom of the system, the Stefan Boltzmann law. And you see that this energy density rises rather quickly and then sort of levels off. The critical temperature, the pseudo-critical temperature, the transition is actually a crossover. The pseudo-critical temperature is now determined by the lattice community with very impressive precision of 1.5 MeV. And is about 156 or 156.5 MeV, and the critical energy density is only something like 340 MeV per cubic Fermi, which is actually less than the energy density in a nucleon. So this is actually a relatively low energy density, and in our collisions we exceed this by a factor of 100 or more. I should say that this blue curve this blue curve here, the solid lines, are calculated in what we call the hadron resonance gas, which essentially is a non-interacting gas of all the hadrons we know in the system. And this will become important, and also non-interacting will become important. So in the dilute limits, then the partition function for QCD can be written as this, the log of that can be written as this log of the sums over partition functions for mesons and baryons. If there would be interaction terms, you would have to add them, but as I said, in the dilute limit, we don't have to do that, and these depend only on temperature and volume and chemical potentials, and to make matter very simple, at large hadron collider energies, all chemical potentials vanish. Of course, at lower energies, one needs to take that into account. For each particle, then, one can express this with familiar formulas, the log of the partition function for each particle. And for each particle, that leads to something which can easily be determined experimentally if we know the momenta and the identity of all the particles. And from this type of description, we'd like to understand what kind of temperature, baryochemical potential, and volume actually is formed with such collisions. In practice, we use the full experimental hadronic mass spectrum, but with vacuum masses, no in-medium masses. And if anybody wants to discuss that, we can do this in the discussion. This is one of the key results. So what is plotted here is the yield measured for the insiders per unit rapidity at central rapidity, and particle species is plotted in this direction. You see red points, these are data points. On this log plot, you don't see any of the uncertainties, because the uncertainties are of the order of 5 to at most 10%, except for the rarest particles. And the blue lines is actually what this type of approach here gives you if you put in a temperature of about 156 MeV and baryochemical potential 0. And you see that actually describes this sequence of measurements here over 9 orders of magnitude with amazing precision. Note that even composite objects like deuterium and their antiparticles and helium hypertriton and helium-4 are very well described. I will come back to this because we want to talk also about loosely bound states. Now, if you look actually closely here in the data over model plot, you see that while overall this fit is very good, you see that there are two outliers. These are the protons, and in fact, this is about a 2.7 sigma deviation, which you could say 2.7 sigma, I don't worry, but since this whole model has been so successful, this has led to many papers trying to understand where this comes from, and we have scratched our head ourselves. Let me show you that actually we now believe that we understand this. And the correction one has to add to this hadron resonance gas is something which should be familiar to all more traditional nuclear physicists, because we take into account the experimentally measured pion-nucleon phase shifts in an approach which was developed in the 60s, in the late 60s by Daschen, Marr, and Bernstein in this paper here, in which essentially for each resonance, for, let's say, the delta resonance or the n-star resonances, for each resonance, one determines the phase shifts from pion-nucleon scattering and then computes the thermal yield of such an interacting resonance, essentially by such an integral here, where the coefficient in that integral is the derivative with respect to mass of this phase shift. Now, if the resonances are very narrow, this derivative becomes a delta function, and you recover the formula which I had before. The reason why we do this is that you see here, for example, the familiar resonances from the pion-nucleon phase shifts. This is actually 15 partial waves for each isospin channel. A whole industry of people worked on that for decades. You see the delta resonance here, and you see how beautifully it fits with a standard resonance, but you see that there are resonances which look very different. For example, this delta 1620. And so there are not only resonant parts in this interaction, but there are also non-resonant parts which one has to take into account. And if we do that, we find a new description with a fit of 156.5 or 6 MeV, a baryochemical potential mu B of 0.7 MeV, but with an uncertainty compatible with 0, and the volume of 4,000 cubic Fermis, and the chi-squared of 19.7 per 19 degrees of freedom. That is, the whole anomaly with protons is completely resolved by using these experimental phase shifts. I have to say that in detail, one has to take into account not only two-body cases, but 3 and higher, and we did this with a particular normalization relative to susceptibilities computed from Lattice Qcd, and you can look it up in this paper here. Now, as I said, at LHC energy, all baryochemical potentials are 0, and you can now see how well actually this kind of thermal picture works if you just look at the yield divided by the spin degeneracy versus mass of the particle. And you see this goes over something like 9 or 10 orders of magnitude. And again, the blue lines, the solid blue lines is our prediction. Actually, if we take into account just the Lattice Qcd statistical operator, this dashed line is if we were to ignore that the hadron resonance gas, of course, is unstable and will have to decay by strong interactions, and that brings you from the dashed line to the solid line. So at LHC energy, matter and antimatter is produced with equal yields. Whether particles have strangeness or not doesn't matter anymore. The only thing what matters is mass, and whether the mass is an omega baryon or a anti-helium-4 is all governed, and leads to this very distinctive thermal pattern. Now, we have done this not only at LHC energy, but from low energies to high energies. You see here the temperature. You see here baryochemical potential. It's not always zero, of course, only at LHC energy. And you see that actually as you increase the beam energy, this temperature from measuring hadrons rises very rapidly, and then around root S of 10 GeV, it levels off and stays constant forever. Actually, we believe that if there would be a future circular collider, and we measure this temperature, or somebody measures this temperature, whenever it will be measured, it will again be on that line, and if not, it would be a major new discovery. We can describe all particle species and their energy dependence, and I think this is also important because this gives us a tool to predict yields of particles with an accuracy of about 10% at any given energy. Now, in the phase diagram here, one of the key results, we plot here temperature and here the measured baryochemical potential, and each of these points is actually essentially a measurement of one full collaboration. This is SIS energies or HES energies, and the top energy is up here at LHC, and you see how these points here actually line up in a characteristic pattern. The shaded area here is what one gets if you take into account Lattice Qcd prediction. Lattice Qcd does not work for large baryochemical potential, but roughly until 200 MeV, these predictions can be taken very seriously. And nowadays, actually, the shaded region has shrunk significantly, in particular in this area here, and is completely consistent with this point. So that means we really have, for the first time, a solid description of what the QCD phase boundary is, at least for relatively small baryochemical potential or very high energies. Now we see that this description for lead-lead collisions does not only stay valid for lead-lead collisions, but there's a very smooth evolution with system size. This is ratio of yields relative to pions from PP to lead-lead, P-lead in between, xenon, xenon in between, and for each of these systems, different particle multiplicities are measured, and you see what kind of systematics we have here, and this, of course, describes the transition from canonical to quant-canonical thermodynamics, and hopefully soon will lead to a universal hadronization description with much, much fewer parameters than is up to now available. Let me come back to a peculiarity. Let me just remind you that we have in this list also a bound state which is called the hypertriton. It's a proton, neutron, and lambda, a state of a proton, neutron, and lambda. The binding energy is about 2 MeV, and the lambda in that state actually has a separation energy of a few hundred keV. And apparently it is still formed at this temperature, characteristic of this temperature of about 155 or 160 MeV, although the binding energy is tiny. This, of course, you can see, I have just listed here the hypertriton. The hypertriton, because this lambda is so loosely bound, has a very large RMS radius. You can see it here, this pink curve compared to the red curve is triton, the triton wave function, and this is the hypertriton wave function. And note the scale for nuclear physics scales. This goes out to 50 or 60 Fermi, and the wave function for the hypertriton goes way out. And nevertheless, this wave function is much bigger in size, the extent of that wave function, than the radius of the fireball, yet it seems to be formed at high temperature. There is a big debate at the moment what that is due to. Let me say that we believe that the binding energy is not a relevant quantity. I show you here for that a comparison between the binding energy, between the transverse momentum spectrum for J psi mesons. This will lead nicely into Johanna's talk. And with the hypertriton, both have the same mass. So thermodynamically, it is an interesting question how they should be related. But for the purpose here, I just want to show that the transverse momentum spectra look pretty much the same, even though the J psi is 600 MeV and the hypertriton is only 2 MeV. So this actually comes from a review which I did recently with Benjamin Dönigus, who unfortunately is ill and therefore not here. But you can already look it up, and all of this is described in some detail there. So, this act sort of gave us enough fuel to think about how this could be that such loosely bound states can actually be formed in nuclear collisions at such high energy and high temperature. And we like to call this, what I will tell you in the following, the doorway state hypothesis. And the idea is that maybe all nuclei and hypernuclei, maybe pentaquark states and also XYZ states are actually not formed in their final hadronic constituents, but as virtual compact multi-quark states at the phase boundary. Recall here that all of these states here seem to follow the same characteristic, only determined by their mass and temperature, and nothing else. Now, this doorway state hypothesis is actually given in our Nature article, but of course the real question is how this can be tested. And in fact, it can be tested by precision measurements of spectra and flow pattern for light nuclei and hypernuclei and all these other states from p-lead to lead-lead collisions, which is clearly a major new opportunity for ALICE 1, 3, and 4 and beyond, but also a new opportunity for measurements at the upcoming GSI FAIR facility and also at the new facility at Dubna, Jena, namely the NICA facility. With that, let me come to my summary. I have shown you that statistical hadronization is a very effective tool to understand the phenomenology of hadron production. It is deeply rooted in the duality between hadrons and quarks near the QCD phase boundary and implies that the QCD statistical operator is actually what governs hadron production in the end. The present precision is mostly limited by the incomplete knowledge of hadron mass spectrums, but I've shown you that with the present measurement precision of about 5%, the deviations which show up for protons are now even quantitatively understood by using experimental pyronucleon phase shifts. And I've also shown you that the yields of light nuclei and hypernuclei can be successfully predicted, and maybe these are produced as quark backs. And as the key result, I would like you to keep in mind that we have really now clearly determined and experimentally located the QCD phase boundary for small baryochemical potential. And this critical temperature is about 156 MeV. Thank you.
Thank you very much, Peter, for this fascinating talk and for congratulations to many of the exciting results you showed here. We have some time for questions. Horst Lenske.
Peter, at one of your transparencies, you said you don't need new physics to explain your results. What does that mean? Does it mean that you exclude new physics, or is it Simply that at freeze out you don't see new physics.
No, no, that means that beyond the QCD phase boundary, there is no additional unknown mechanisms in this, but that we actually understand the hadron production quantitatively from the QCD statistical operator, which contains, of course, the transition from hadron physics to quark-gluon plasma. So that's what is meant by that.
In other words, you don't exclude new physics.
Well, I don't know what new physics is in that sense. It was a reference to something which is not so relevant anymore. And, but the new physics, if you like, is that we have measured and clearly determined the QCD phase boundary now with precision. And that part, I think, is, if you like, new physics, but it is not new physics in the, let's say, new particle discovery sense, but equally important.
Any other questions? Hermann Wolter?
Your last sentence here is interesting, where you say a coalescence approach is not enough.
Yes.
Can you explain that a little
Yes.
bit more? Because that would say that there are correlations already before these things are frozen out.
Maybe, and that, of course, is a big argument, but let me give you a little bit of an idea why I said this. And I put the sentence here exactly to get a question of the type which I am now getting. Take the hypertriton. The hypertriton is a very loosely bound state. Actually, if you take 10 momentum transfer of the order of 10 MeV over c, it already breaks up. Now, in coalescence, to form actually a bound state from coalescence does not work in vacuum because it violates energy conservation. So the standard argument is, I couldn't care less, doesn't matter, there are lots of particles around, and they will somehow, nobody knows how, but somehow solve this problem of energy conservation. However, if you go to, and that may work in a certain sense for the deuteron, but for the hypertriton, the actual act of keeping the getting the momentum conservation right actually destroys the hypertriton. Because this is a collision. You have to have a collision with the third particle. So what that means is, and secondly, the hypertriton is so loosely bound that it actually, if you do it in this coalescence idea, it can only take place when there's no other particle around, because it is a huge particle. So it is clear that this idea of coalescence, which looked like reasonable if you could neglect all of these issues of energy conservation and so on, if you take it for such loosely bound states, loses its meaning. And we would need a much more detailed theory, a multi-particle theory, if you want to use something similar to really do this correctly.
You need more than a single particle distribution function.
Yeah, but the problem is this object itself is so loosely bound that if, for example, a pion would hit it to somehow restore energy conservation, the whole system breaks up. And that you would have to somehow take into account. The cross-section, the inelastic cross-section for hypertriton pion is roughly 1 barn. Not measured, but guessed. Okay.
Okay, thank you very much. I'm afraid in the interest of time, while we could go on a lot longer, we will thank Peter again. Congratulations. Thank you, Peter. And continue with